Hi, and welcome to 2.6c Kinematic Equations 3, where we'll do the last kinematic equation. In this lesson, just like all the other ones, you'll be able to use kinematic equations to calculate a bunch of stuff. Time to derive the last equation. So let's say we know the initial velocity, we know the distance traveled, and the acceleration of a sloth. Look at that nice, cute sloth. Even though we don't have the time, we should still be able to find the final velocity. So we're looking for the final velocity, and in this case, we don't care about the time. We need an equation with these four variables and not time. So let's combine these two equations. We have VF equals VI plus AT, and we have D equals 1/2 VF plus VI times T. So, excuse me, Mr. Sloth, I need some room to derive the equation. See you later. He's always so slow to move, that sloth. Okay, so let's derive, if we want to get rid of T, let's solve for T in this formula, and then we'll plug that value in over here, and then we'll have an equation that doesn't have any T in it because we solved. So we'll do VF minus VI. We'll swing that VI to the other side by subtracting it, is equal to A times T. And now we have T is equal to VF minus VI divided by A. So anywhere we see a T, we're actually going to plug in, hey, this is equivalent to T. So why don't you just plug it in over there, and then we'll be left with an equation that doesn't have T in it. So we're going to do that. D is equal to 1/2 VF plus VI times T, but T could also be said as VF minus VI divided by A. And now our job is technically done. But it would be dumb if we left it like that because look how messy that looks, okay? So instead, let's get rid of these fractions. Let's start by cleaning it up by getting rid of those fractions. And how do you do that? Well, the A is in the denominator, so I'm going to multiply by A in the numerator, and that'll cancel out. So we have, and then whatever you do to one side, you have to do to the other in order to maintain this equalness. So technically we have AD is equal to 1/2 VF plus VI, and then this is just VF minus VI. And we still got that 1/2 there, so let's do the same thing by multiplying by 2. So if you do 1/2 times 5, let's say this is 5 instead, times 2, it just the 2 and the 1/2 cancel out. That's my point. So you just get 5. So you multiply by 2 on this side, and now we have 2AD, ooh, that's kind of nice, is equal to this weird thing, VF plus VI, VF minus VI, in parentheses, and you might recognize this. We're going to do some FOIL, and you know this is the plus and this is the minus, so you could already kind of predict what it might look like. But I'll do the whole thing out just as a refresher. So this is we'll do the first. So FOIL stands for first, outer, inner, last. So first becomes VF times VF, or VF squared, right? VF times VF. And then VF times negative VI becomes minus VF times VI, because those are two different terms. They look like it's all the same, but look at the subscripts. So first, and then we'll do the outer. Oh, I already did that, outer. And then we'll do the inner. So the inner is VI times VF. So that becomes positive. They're both positive. VF times VI. I'm writing it in that order so that we could see, ooh, those are going to cancel out. You already knew that, right? And then we'll do the last. I was getting ahead of myself there. VI times negative VI becomes minus VI squared. VI times negative VI. So yeah, negative VF VI plus VF VI. Those two things cancel out. And you're left with 2AD is equal to, then we're left with just VF squared minus VI squared. That's pretty good. That's pretty good. But I don't like this VF minus VI squared thing. I'd rather have things be positive. I want to be positive, right? So let's add VI squared to both sides, and you're left with VF squared is equal to VI squared plus 2AD. And look at that. That is a nice equation, and it does roll off the tongue. VF squared equals VI squared plus 2AD. You're going to be writing that down a bunch of times. There it is in all its glory. Let's find it on the reference table, shall we? That's our last tool in the tool chest of kinematic equations. All right, so take a look. You probably think it's on the back page. You would be right. You probably saw it before. All right, we're talking about this one right here. And now we have these are like cool kinematic equations. This one is just the acceleration formula reworded. This is the definition of acceleration. This is like the definition of average velocity, the displacement divided by the time. So the top two aren't that exciting to me. This one is like, okay, that's pretty cool. But then we have these, and that's pretty cool. But don't forget, also we have d is equal to 1/2 vf plus vi times t. So now, just looking at these four, we have equations for almost every scenario. This doesn't look like an equal. Okay, so what variable is not here? This is when you don't have displacement. What variable is not in this one? This one is when you don't have VF and you're not looking for it. What variable is not here? We just did it. All right. This is when you don't have time. They don't give you the time, and they don't even give you the time of day, and they're not even asking for the time. So why would you want time to be in your equation? I wouldn't. And then what is not in the secret formula? That's the acceleration. Everybody likes acceleration. That's why it's not on there, is because they're like, hey, acceleration isn't included in that one. Let's leave it off. No, I'm just kidding. I don't know why they didn't put there. It's just a combination of the average velocity and the average velocity, VF plus VI divided by 2. So that's just an overview. Let's do some examples. It says the fastest land animal is the cheetah, which has a recorded speed of 28.5 meters per second, or 75 miles an hour. That is insane. That's even faster than Mr. Nangle. That's crazy. The cheetah is running at top speed before decelerating at -2 meters per second squared. So be careful. I know we want to use the miles per hour one, but we're going to use these because the meters and the seconds agree better than the miles and the hours over a distance of, and then 100 meters again. So what is the cheetah's speed after this deceleration? Excuse me, Mr. Cheetah, please get out of the way. Thank you very much. Okay, so let's do the guess method. One piece of given information is the initial velocity, 28.5 meters per second. And then the acceleration is in the opposite direction. It's in the negative direction because it says in the problem we're slowing down over a distance of 100 meters. And they want to know, what is the cheetah's speed, final velocity, after it slows down for a bit? Does it come to a stop? Does it start moving in the opposite direction? Let's find out. So we're going to find the equation that does not have t in it, which we just derived, and we looked at our reference table, and it is VF squared is equal to VI squared plus 2AD. Now we could plug in, well, we're looking for VF, so that's cool. VI is 28.5. We wrote our units on the side, so we don't have to put them in the equation. Mr. Nangle will give you full points. 2 times A is -2. Don't forget the negative. Now, especially with this equation, or in general, and then D is 100. Why am I saying this equation? Because see how it's these two terms adding together? Well, as soon as you make this a minus, you're not adding anymore. You're going to end up subtracting. So that's going to change your answer. If you make this positive instead, you'll get a completely different answer. The magnitude will not be correct. So you want to make sure you're using positive and negative signs to indicate the direction, and don't forget about them. So you do the math and you get VF squared is equal to 412.25, and then you realize that that can't possibly be the answer because that would be very fast and you're supposed to be slowing down, so you have to take the square root of both sides because it's VF squared and we just want VF, not VF squared. So you do the square root and you get about 20.3 meters per second, which is still very fast. I'm pretty sure that's greater than my top speed, even on a good day. Okay, so that's it. Last one, we have a practice problem. Feel free to pause the video, try it on your own, and then watch the answer. So you can pause it here if you would like. The peregrine falcon is the fastest bird and the fastest member of the animal kingdom with a speed of 108 meters per second. The falcon accelerates at a rate of 9.8 meters per second squared to this top speed from rest. How far does the falcon travel as it accelerates? All right, excuse me, falcons. Thank you. So we have the guess method. All right, the final velocity is 108 meters per second. VF is equal to 108 meters per second. How do I know it's the final velocity? Because it says the falcon accelerates to this top speed from rest. So you're coming from a resting position where your initial velocity is 0 meters per second. So there's your like hidden information in the problem. This is not a number, so it doesn't jump out at you like these numbers will. You're going to have to read the problem and interpret it and say, oh, I can plug that into my equation because I know it is a number. It's 0. And it's accelerating, so that's cool. They tell you flat out 9.8 meters per second squared. And we want to speed up, so they're agreeing in their direction, so that's cool. And they're saying how far does it travel. And again, I would look at this and say, hey, I don't care about time. Make sure when I'm looking at it, at my equations in the reference table, time is not part of the equation. So then you'll get VF squared equals VI squared plus 2AD. Now we know VF, 108 squared, is equal to, this is 0 squared. Now some people just go like that. That's totally cool. You could do that. I like to plug in the numbers just because I do the same process every single time. That way I know I'm not skipping a step by mistake. I just do the same exact thing every single time. I plug the numbers right in, all right, no matter what equation it is. Now we can solve. And you get 11,664 is equal to, this should be 19.6 times D. Get used to seeing this number. It's going to pop up again, and then you divide, and you get the displacement is equal to 595.1 meters. Don't forget the units in the answer. So that's pretty far. That's like almost 6 football fields that it goes through that decelerate. Wouldn't it be nice to be a falcon and just like be flying around? Maybe one day I'll be a falcon. No, probably not. Anyway, that's about it. Thanks for watching. Have a great day.